Hello and welcome to our presentation of What's the Price? Predicting the cost of healthcare insurance given various factors. Health insurance helps pay for medical expenses. It works by pooling resources from other policyholders to spread the financial risk by protecting those requiring medical attention from paying the full costs associated with major medical expenses. Whether purchased privately or funded by the government, medical insurance is essential to providing protection against increasing medical costs. The Affordable Care Act of 2010 was designed to extend health insurance to those who could not afford it. However, costs continue to grow. There are many factors that drive the increasing costs of health insurance, some of which are directly related to the personal attributes of the policyholder. We use data to determine which attributes contribute most. Based on these attributes, we used a regression model to predict the expected cost of health insurance. We obtained our data from Kaggle. It contained 1,338 observations with the following variables: age, which is the age of the policyholder; sex, which is a binary variable indicating whether the policyholder is male or female; BMI, which is the body mass index of the policyholder. It's calculated using their weight in kilograms divided by the square of their height in meters; children, which is the number of children insured through the insurance policy; smoker, which is a binary variable indicating whether the policyholder smokes or not; region indicates where the policyholder resides. It's a categorical variable with 4 classes: Northeast, Northwest, Southeast, and Southwest. And finally, charges, which is the cost of health insurance in dollars. It is also our target variable. We converted the binary variables, sex and smoker, into binary labels, where sex equals 0 indicates female, and sex equals 1 indicates male, and smoker equals 0 indicates the policyholder does not smoke, and smoker equals 1 indicates that they do. We also converted the categorical variable region into encoded labels where region equals 0, 1, 2, and 3 for Northeast, Northwest, Southeast, and Southwest, respectively. We transformed the continuous variable BMI into a categorical variable using the CDC guidelines, which indicate BMIs less than 18.5 are classified as underweight, BMIs between 18.5 and 25 as normal, BMIs between 25 and 30 as overweight, and BMIs 30 and above as obese. From here, we converted the categorical variable into encoded labels where BMI equals 0, 1, 2, and 3 for underweight, normal, overweight, and obese, respectively. When a spouse or children are added to an insurance plan, the price increases. However, many insurance companies only charge for a maximum of 3 children. So we binned observations with more than 3 children into the same category as those with 3, where children equals 3 indicates 3 or more children. Once we prepared our data, we created histograms of the numerical and bar plots of the categorical variables. The ages range from 18 to 64 with a mean age of 39. Children originally ranged from 0 to 5, but now range from 0 to 3 after our transformation. There are 574 observations without children, 324 with 1 child, 240 with 2 children, and 200 with 3 or more children. Sex contains 676 males and 662 females. Region contains 324 from the Northeast, 325 from the Northwest, 364 from the Southeast, and 325 from the Southwest. Smoker contains 274 smokers and 1,064 non-smokers. BMI contains 20 underweight, 225 normal, 386 overweight, and 707 obese observations. We also created scatter plots of the variables against charges. In the age versus charges scatter plot, we noticed 3 distinct groups, each showing a positive linear relationship, with charges slightly increasing as age increased. We also noticed charges were generally higher for smokers versus non-smokers, and those with higher BMIs. However, charges by sex, children, and region appeared consistent regardless of charges. We removed these consistent variables, sex, children, and region, and modified the age versus charges and BMI versus charges scatter plots to include smoker as a third dimension. We observe smokers are generally charged more, regardless of age. Also, smokers who have higher BMIs are generally charged more. We created a similar scatter plot as before, but with BMI as a continuous variable, as it originally appeared in the data. We noticed a linear relationship between BMI and charges for smokers.
Variable selection. So after analyzing our data sets, we found that the most significant variables were that of the age, the smoker, and the BMI. So this plot just shows the variables against their levels of importance, with smoker being the most important. And although age and BMI look really close, BMI is slightly more important than the age. So what do we do with this data? This is just to visualize it to kind of show the levels of importance, but then we further took our data and split into a training, validation, and test sets. So how do we do this split? We split the data evenly, somewhat evenly, 50% going towards our training set, and the other 50% allocated equally between the test and validation sets. That's each set having 25% of the data. So what did we do next? We trained the decision tree regression model against our training data with a BMI in categorical form. And this chart here just shows the results from that. It's showing the scores against all the variables. We then move forward and trained the decision tree model on our training data using BMI as a continuous variable, and these were the results as shown. So we can see the plots, we can see the scores. So what we did after analyzing the results, we decided to select the smoker, the BMI as a continuous variable, and the age as the variables to use in our regression model. Now, to understand how to properly interpret the regression model, the scores you might get, we decided to put a little explanation of the parameters just so there's an understanding of what these scores mean. Now, as you can see, the R square is a statistical measure that represents the proportion of the variance for a dependent variable that is explained by an independent variable or variables in a regression model. This is, you might think this is similar to correlation, but this is not exactly the case. Correlation explains the strength and relationship between an independent and dependent variable, but the R squared explains to what extent one variable varies in terms of the other variable, if that makes sense. And then the other measure was the MAE. The MAE measures the average magnitude of the errors in the sets of forecasts without considering their direction. It just measures the accuracy for continuous variables. So these were our parameters for regression. So we trained and fit three different regression models on our validation data, and we decided to use the R squared and the MAE metrics to evaluate our models, and we obtained the following results and put them in a table. So from the linear regression, we can see the R squared and the MAE, from the decision tree as well, and from the random forest regression. So we can see the best results came from the random forest regression, so that's the model we're going to go with. So the next step was the parameter tuning. So choosing our parameters for a random forest, we performed a cross-validation grid search to find values that resulted in the best MAE score. Now see, because the criteria, so we set the criteria into MAE, the max depth to 4, max features none, minimum samples leave 3, minimum sample split 4, number estimators were 200. Now, what do we do with these parameters? We use these parameters to train the random forest, and with the training and validation data, we fit it on our test data. The results we obtained were an R squared score of 0.86 and an MAE score of 2022.03. So what does this mean? The resulting using the fine-tuned random forest shows increased performance on both performance metrics. So it produced a better R square and a better MAE than previously. So this is proof that sometimes tuned parameters can lead to more accurate results.
The R squared value that we obtained indicates that 86% of our data fit the random forest regression model, and the mean absolute error indicates that our prediction is off by $2,022.03 on average.
So in conclusion, based on the regression models we used, we saw improved prediction when using the fine-tuned random forest model. This is what I just said about fine-tuning parameters to get better results. There are also other models that there would have been an increased performance in because we didn't take the fine-tuned parameters and run them through all. We just ran them through the one that was best for us. So, if anything, to consider for the future, you could also take the fine-tuned parameters and run them through and try all the other models you tried before just to see which one's actually the best one for you. Also, our analysis and predictions were limited to the variables in our data set. So, because we know that there are definitely more factors that contribute to health insurance than just the age, the smoker, the BMI, number of children. So yeah, but we just had to work with what we had. So these results are solely based on what we had. So some other factors that could affect health insurance were whether or not the spouse is on the plan, whether the policyholder has a secondary health insurance, whether or not the insurance is provided by an employer, Medicare, Medicaid, Affordable Care Act, or anything else. It depends on the insurance company because the insurance premiums vary by company. The type of insurance plan, that's also a key factor. That wasn't included here. These are just other things, real world things that we know could affect the price. And another thing is whether or not the people have a chronic disease or illness. So these are all factors that could affect the health insurance premium. But like we said, we're going based off of what we had. So thank you, and I hope you enjoyed our presentation.